13.8 billion years ago, something impossible happened. Not just unlikely, not just improbable, impossible. Every law of physics we understand says it couldn't occur. Every equation breaks down. Every calculation returns infinity. And yet, here we are, you, me, the earth beneath our feet, the stars above our heads, all of it emerging from an event that defies the very rules that govern our existence. What if I told you that before time existed, something created time? That before space existed, something created space? That the universe didn't expand into anything, but rather, space itself came into being. The evidence for this cosmic impossibility surrounds us. It's in the light from distant galaxies. It's in the static on old television sets. It's encoded in the very atoms that make up your body. Today, we journey through evidence that challenges everything we thought we knew about existence itself. We'll witness the moment of creation. We'll watch as the universe transformed from a seething ocean of energy into the magnificent cosmic architecture we inhabit. We'll discover how scientists pieced together the story of our cosmic birth, not through speculation, but through meticulous observation and brilliant detective work. Prepare yourselves. We begin. The discovery. The story begins not with a telescope, but with a discovery that seemed utterly mundane. In 1964, two radio astronomers at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to eliminate an annoying hiss from their antenna. This persistent static was ruining their observations. They checked everything. They cleaned pigeon droppings from the antenna. They pointed it in every direction. The hiss never went away. No matter where they aimed their instrument, north, south, east, west, up, down, the noise remained. Always the same intensity. Always the same frequency. Uniform across the entire sky. What Penzias and Wilson had accidentally discovered was the afterglow of creation itself. But to understand why this mattered, we need to rewind further to 1927 to a Belgian priest and physicist named Georges Lemaitre. Lemaitre had been studying Einstein's equations of general relativity, and he found something Einstein himself had missed. The equations suggested that the universe wasn't static. It was expanding. And if the universe was expanding now, Lemaitre reasoned, then in the past, it must have been smaller, much smaller. He traced this expansion backward in time, following the mathematics to its logical conclusion. And what he found shook him to his core. If you ran time backward far enough, everything in the universe, all matter, all energy, all of space itself, contracted down to what he called a primeval atom, a point of infinite density from which everything emerged. The scientific establishment was horrified. Einstein himself rejected the idea initially, calling it abominable physics. The British astronomer Fred Hoyle mockingly dubbed it the Big Bang, a name intended as ridicule, but which stuck forever. Why the resistance? Because Lemaitre's model implied something deeply uncomfortable. The universe had a beginning. There was a moment of creation. Before that moment, if before even makes sense, nothing existed. Not darkness, not emptiness, not even time itself. This sounded too much like theology for the comfort of many scientists. But then observations began rolling in that couldn't be ignored. In 1929, Edwin Hubble, working at Mount Wilson Observatory in California, made a startling discovery. He measured the light from distant galaxies and found something extraordinary. Galaxies farther away were moving away from us faster than nearby ones. Not just moving away, accelerating away. Imagine drawing dots on a balloon and then inflating it. Every dot moves away from every other dot. The farther apart two dots are, the faster they separate. This is precisely what Hubble observed with galaxies. The universe was expanding, exactly as Lemaitre had predicted. The mathematics was beautiful and terrifying. If galaxies are flying apart now, then in the past they were closer together. Run the clock back far enough, and everything in the observable universe, 100 billion galaxies, each containing hundreds of billions of stars, was compressed into a region smaller than a single atom. But here's where it gets truly mind-bending. The Big Bang wasn't an explosion in space. There was no space to explode into. The Big Bang was the explosive expansion of space itself. Space, time, matter, and energy all came into existence together in the same instant. Think about that. It's not that the universe expanded into a pre-existing emptiness. Space itself stretched, carrying matter along with it. The universe didn't explode outward from a center. It exploded outward from everywhere simultaneously. So what would such an event look like? What evidence would it leave behind? Lemaitre and later physicists like George Gamow realized something crucial. If the universe began in an incredibly hot, dense state, it would have been filled with intense radiation. As the universe expanded, this radiation would cool, but it would never disappear. It would stretch out, its wavelength lengthening as space itself expanded. They predicted that this primordial radiation should still exist today, cooled to just a few degrees above absolute zero, permeating all of space. In 1948, Gamow's colleagues Ralph Alpher and Robert Herman calculated the exact temperature, approximately 5 degrees Kelvin. For 16 years, no one bothered to look for it, until Penzias and Wilson, trying to eliminate that infernal hiss, discovered they had detected it by accident. The hiss wasn't interference. It wasn't pigeons. It was the echo of creation, light, that had been traveling through space for 13.8 billion years, cooled from trillions of degrees to 2.7 degrees above absolute zero. They were detecting photons that had been released when the universe was just 380,000 years old, when space became transparent for the first time. Before that moment, the universe was so hot and dense that light couldn't travel through it, like trying to see through fog. this discovery, the cosmic microwave background radiation, remains the most powerful evidence for the Big Bang. But the evidence forces us to confront an uncomfortable possibility. If we can trace the universe back to a beginning, what caused that beginning? And what came before? Accumulating evidence, observable signatures. The cosmic microwave background was just the beginning. As technology improved, scientists discovered that this ancient light contains a treasure map, a detailed blueprint of the infant universe encoded in subtle temperature variations. When NASA launched the Cosmic Background Explorer satellite in 1989, it measured these temperature variations with unprecedented precision. What it found was extraordinary. The background radiation wasn't perfectly uniform. It contained tiny fluctuations, regions just 0.001% hotter or cooler than average. These ripples represented quantum fluctuations from the first moments after the Big Bang, blown up to cosmic scales by the expansion of space. Think of these ripples as seeds. The slightly denser regions had stronger gravity, pulling in more matter. Over hundreds of millions of years, these seeds grew into the galaxies, galaxy clusters, and vast cosmic structures we see today. The pattern of these fluctuations matches theoretical predictions with stunning accuracy. The universe, at 380,000 years old, looked exactly as the Big Bang model predicted it should. But scientists discovered something else in this ancient light, something that revealed secrets about what the universe is actually made of. In 2001, the Wilkinson Microwave Anisotropy Probe provided even more detailed measurements. By analyzing the size and distribution of the temperature ripples, scientists could calculate the universe's composition with remarkable precision. The results were shocking. Ordinary matter, the stuff that makes up stars, planets, and us, accounts for only 5% of the universe's total mass energy. 5%. Everything we can see and touch is a cosmic rounding error. 27% is dark matter, a mysterious substance that doesn't interact with light, but exerts gravitational pull. The remaining 68% is dark energy, an even more mysterious force causing the universe's expansion to accelerate. We live in a universe where 95% of existence is invisible to us. But there's more evidence, and it comes from the elements themselves. In the 1940s, physicist Ralph Alpher worked out what should have happened in the first few minutes after the Big Bang. The universe was so hot that atomic nuclei couldn't hold together. Everything existed as a soup of protons, neutrons, and electrons. As the universe expanded and cooled, Alpher predicted that nuclear fusion would occur for just a brief window, roughly 3 minutes, creating helium from hydrogen. After that, the universe would cool too much for fusion to continue. He calculated that this primordial nucleosynthesis should produce a universe that's roughly 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium. And what do we observe when we look at the oldest stars in the universe? Stars that formed from pristine material before any stellar processing occurred. 75% hydrogen, 25% helium, exactly as predicted. This isn't a coincidence you can hand wave away. The precise ratios of light elements throughout the universe match Big Bang predictions to extraordinary accuracy. No other theory can explain this, but this represents just one piece of a much larger puzzle, hidden in the architecture of the cosmos itself. Deeper implications. The deeper scientists looked, the stranger the evidence became. When astronomers measured the expansion rate of the universe using distant supernovae in 1998, they expected to find that gravity was slowing the expansion. After all, every galaxy pulls on every other galaxy. What they discovered instead won them the Nobel Prize and terrified cosmologists. The universe's expansion isn't slowing down, it's speeding up. Imagine throwing a ball into the air, and instead of falling back down, it accelerates upward faster and faster. That's what the universe is doing. Something is pushing galaxies apart with ever-increasing force. This discovery forced scientists to add dark energy to their models, a mysterious component that acts like anti-gravity, pushing space apart. The evidence suggests that dark energy has dominated the universe for the past 5 billion years, and its dominance is increasing. But here's what keeps cosmologists awake at night. We have no idea what dark energy actually is. The leading theory suggests it's a property of space itself, that empty space has energy. And as the universe creates more space through expansion, it creates more dark energy, which drives faster expansion, which creates more space. A runaway process. The implications are staggering. The evidence extends beyond simple expansion into the realm of cosmic structure itself. When scientists mapped the distribution of galaxies across billions of light years, they found something unexpected. Galaxies aren't scattered randomly through space. They're organized into an immense cosmic web, vast filaments of galaxies separated by enormous voids. This structure contains information about the universe's earliest moments, computer simulations that start from Big Bang initial conditions and evolve forward using known physics, reproduce this cosmic web perfectly. The filaments, the voids, the clusters, all of it emerges naturally from those quantum fluctuations in the early universe. But the most remarkable discovery involves looking back through time itself. Light travels at a finite speed, 299,792 kilometers per second. This means when we look at distant objects, we're seeing them as they were in the past. The farther away something is, the further back in time we're looking. Using the Hubble Space Telescope and later the James Webb Space Telescope, astronomers have observed galaxies whose light has been traveling for more than 13 billion years. We're seeing them as they appeared when the universe was less than 1 billion years old. And what we see matches Big Bang predictions with eerie precision. These early galaxies are different from modern ones. They're smaller, more chaotic, richer in gas, and deficient in heavy elements. We're literally watching galaxy evolution in action, observing the universe's childhood. The James Webb Space Telescope, launched in 2021, has pushed even further back. It's detecting galaxies that formed just 200-300 million years after the Big Bang. These proto-galaxies are witnessing the transition from the cosmic dark ages, when no stars yet existed, to the epoch when the first stars ignited, flooding the universe with light for the first time. Every observation confirms the narrative. The universe had a beginning, and we can trace its evolution from that moment to today. The evidence extends beyond galaxies into the realm of space and time themselves, forcing us to confront questions that push the boundaries of physics. The big picture, theoretical framework. So what actually happened at the moment of creation? According to our best current theory, the universe began not with a bang, but with a period of exponential expansion called cosmic inflation. In a fraction of a second, specifically between 1036 and 1032 seconds after time began, the universe expanded by a factor of at least 1026. To put that in perspective, imagine a marble expanding to the size of the observable universe in less time than it takes light to cross an atomic nucleus. This isn't speculation. Inflation solves several critical problems with the Big Bang model. First, the horizon problem. The cosmic microwave background has the same temperature in opposite directions of the sky regions that, without inflation, would never have been in contact, never able to reach thermal equilibrium. How did they end up at the same temperature? Inflation provides the answer. Before inflating, these regions were in contact. Inflation then stretched them across the cosmos faster than light could travel. Second, the flatness problem. The universe appears geometrically flat on cosmic scales. Parallel lines stay parallel forever. But in general relativity, any deviation from perfect flatness grows rapidly over time. For the universe to be as flat as we observe today, it must have been incredibly, impossibly flat in the early universe. Unless inflation occurred. Inflation stretches space so dramatically that any initial curvature gets smoothed out, like inflating a wrinkled balloon until its surface appears flat. The theory was proposed by physicist Alan Guth in 1980 and refined by Andre Linde, Paul Steinhardt, and others. It suggests that inflation was driven by a quantum field in a high energy state. When this field decayed to a lower energy state, its energy converted into matter and radiation, the hot Big Bang. This means the Big Bang itself wasn't the beginning. It was what happened when inflation ended. Think about that. The hot, dense state we call the Big Bang, the moment from which we date the universe's age, was already the result of a previous process. Leading physicists like Max Tegmark at MIT and Sean Carroll at Johns Hopkins argue that inflation also explains the quantum fluctuations that seeded cosmic structure. Quantum uncertainties in the inflation field got stretched to cosmic scales, becoming the density variations we see in the cosmic microwave background. This forces us to reconsider fundamental assumptions about reality. The universe we observe, all 93 billion light years of it, may have originated from a quantum fluctuation smaller than a proton. The very fact that we exist traces back to quantum uncertainty made manifest at cosmic scales. But inflation creates as many questions as it answers, particularly about what lies beyond our cosmic horizon. Part B: Future implications. Recent breakthroughs suggest we're on the verge of testing these ideas directly. The European Space Agency's Euclid mission, launched in 2023, is mapping the distribution of dark matter and dark energy across cosmic history. By observing how the cosmic web evolved over time, scientists hope to constrain models of dark energy and test whether it's truly constant or changing. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will push these observations even further, potentially revealing whether dark energy is a cosmological constant or something more exotic, a field that evolves over time. But the most exciting possibilities involve detecting primordial gravitational waves, ripples in space-time itself generated during inflation. Einstein's general relativity predicts that accelerating masses create gravitational waves. Inflation, with its exponential expansion, should have generated a background of gravitational waves that still permeate the universe today. Several experiments are hunting for these waves. The BICEP and Keck arrays at the South Pole search for their imprint in the polarization of the cosmic microwave background. The proposed LISA mission, a space-based gravitational wave detector, would detect low-frequency gravitational waves from the early universe. Finding primordial gravitational waves would be revolutionary. It would confirm inflation occurred and tell us the energy scale at which it happened. It might even provide clues about physics beyond the standard model, the theory of fundamental particles and forces. Some physicists, like Avi Loeb at Harvard, propose even more ambitious observations. If inflation created bubble universes beyond our cosmic horizon regions that underwent different inflation processes, we might detect evidence if one of these bubbles collided with ours in the distant past. Such a collision would leave a distinctive pattern in the cosmic microwave background, a circular discontinuity, like a bruise on the sky. No such bruise has been found yet, but we're looking. What this means for us extends beyond physics into philosophy. The Big Bang model tells us that we live in a universe with a finite age, finite size, and finite lifetime. Every atom in your body was forged either in the Big Bang or in the heart of a star. You are literally made of stardust, remnants of stars that exploded billions of years ago, scattering their enriched material into space, where it eventually coalesced into our solar system. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it was created through nuclear fusion in stellar cores or during supernova explosions. We are not separate from the universe. We are the universe examining itself, and the story continues. The universe hasn't finished evolving. It's still expanding, still cooling, still creating new structures. 5 billion years from now, our Milky Way galaxy will collide with the Andromeda galaxy, forming a new, larger galaxy. Tens of billions of years from now, the last stars will burn out. Trillions of years from now, even black holes will evaporate through Hawking radiation. The universe that gave birth to us will continue its transformation long after we're gone. The ultimate questions, the most profound implications emerge when we consider what the Big Bang model really tells us about existence. If the universe had a beginning, what caused it? What existed before? These questions push us to the edge of science and into philosophy. Some physicists, like Stephen Hawking, argued that before the Big Bang is a meaningless concept, like asking what's north of the North Pole. Time itself began with the Big Bang. There is no before because time didn't exist. Other physicists aren't satisfied with this answer. Quantum mechanics suggests that nothing is truly stable. Even empty space seethes with quantum fluctuations, particle-antiparticle pairs that pop into existence and annihilate in fractions of a second. Physicist Alexander Vilenkin proposed that the universe itself might have emerged from such a quantum fluctuation, a universe from nothing. But this raises deeper questions. If the universe can arise spontaneously from quantum fluctuations, why don't we see new universes forming around us all the time? What selected the particular laws of physics our universe follows? Some physicists invoke the anthropic principle. We observe this particular universe with these particular laws because only this type of universe can produce observers like us. In universes with different physics, stars might not form, or atoms might not be stable, or chemistry might be impossible. This leads to perhaps the most mind-bending possibility: eternal inflation. According to this model, proposed by physicists like Andre Linde, inflation never truly ends. It stops in some regions like ours, creating pocket universes with their own Big Bangs. in other regions, inflation continues, spawning more pocket universes, which spawn more endlessly. If this is true, our universe, everything we can observe, is just one bubble in an infinite, eternally inflating multiverse. Each pocket universe might have different physical laws, different constants of nature, different types of particles and forces. We would inhabit just one universe among infinite variations. The evidence suggests a cosmos far stranger than our ancestors imagined. Not a static, eternal universe, but a dynamic, evolving one with a definite beginning and potentially a finite future. Not a cosmos designed specifically for us, but one where we happen to exist because the conditions allow it. And yet, for all we've learned, profound mysteries remain. What is dark energy? What is dark matter? What drove inflation? Why did the universe begin with the particular initial conditions it had? Why do the laws of physics take the form they do? The Big Bang model is the most successful scientific theory ever proposed for understanding cosmic origins. It makes testable predictions that have been confirmed countless times. But it's not the final answer. It can't be. It doesn't explain what came before, or why the universe exists at all. Perhaps the deepest question is this: why is there something rather than nothing? The Big Bang traces the universe back to a beginning, but it doesn't explain that beginning. It tells us how the universe evolved, but not why it exists. Maybe that question lies forever beyond science, in the realm of philosophy or theology. Or maybe future observations, gravitational waves from the quantum birth of the universe, evidence of bubble universe collisions, or discoveries we can't yet imagine will point toward answers. We've journeyed from a mysterious hiss in a radio antenna to the edge of existence itself. The evidence is overwhelming. 13.8 billion years ago, the universe began in an event of unimaginable energy and has been expanding and evolving ever since. We've detected the afterglow of creation. We've measured the universe's composition. We've watched galaxies form and evolve across billions of years. The Big Bang isn't speculation or philosophy. It's an observational fact, confirmed by multiple independent lines of evidence. And yet, the more we learn, the more mysteries emerge. The current scientific consensus holds that the universe began with a period of rapid inflation, followed by the hot Big Bang, followed by 13.8 billion years of expansion and structure formation, leading to the cosmos we inhabit today. The evidence supporting this model is as solid as any scientific theory can be. But cosmologists continue searching for deeper understanding. They seek the quantum theory of gravity that will describe the first moments of existence. They hunt for dark matter particles in underground detectors. They map the cosmic web to understand dark energy. Each answer reveals new questions. Each solved mystery uncovers deeper ones. Perhaps that's the most profound revelation of all. We, conscious matter shaped by 13.8 billion years of cosmic evolution, have traced our origins back to the first moments of time. We've deciphered the universe's history written in ancient light and distant galaxies. We've confronted the deepest questions about existence, and we're just beginning. The universe is vast. The mysteries are endless.